And then there's the answer.
I'm not a karaoke person.
You're no
Yeah.
Oh, the trash here.
Well, I need to get up. You do need to get up to your presence. Yeah, my wife
Okay, everyone? Is this thing working? Okay, hi everyone. It's 3 p.m., so let's get started promptly. So it is my pleasure to introduce our colloquium speaker, Julianne Dalcanton. Julianne is the director of the Flatiron Institute Center for Computational Astrophysics in New York City. Prior to joining the foundation, she was a professor and chair of astronomy at the University of Washington. She obtained her PhD in astrophysical sciences from Princeton University and her bachelor's in physics from MIT. And she did her postdoctoral training as a Hubble Fellow at the Carnegie Observatories in Pasadena, California. Julianne is known for her innovative work, furthering our understanding of the origins and evolutions of galaxies, particularly via the study of resolved stellar populations and the ISM in nearby galaxies. Her significant contributions have been acknowledged by various awards and fellowships, including, for example, the Beatrice Tinsey Prize from the AAS. And Julianne is especially well known as one of the single largest users of the Hubble Space Telescope, most notably as the PI of the large HST multi-cycle treasury program, which is known as the Panchromatic Hubble Andromeda Treasury, or FAT survey. More recently, Julianne has been known as being the #1 biggest fan of ARP galaxies, and also her phenomenal karaoke performances in Manhattan. So today she'll be telling us about her work on stellar populations in the ISM, which involves small scales yet big fun. Please join me in welcoming Julianne.
Hi, I'm super happy to be here. Let's speed run some science. Okay, so to just kind of frame like why I'm doing, like this has been my dream for like well over a decade. For me, like I'm super interested in like astrophysics, and some of the most interesting stuff for me personally is the stuff that's happening at sort of astrophysically small scales. There's a lot of work we do that's like broad characterization of stuff in the universe, super important. But then I'm like kind of interested in like what's going on underneath the hood that leads to this emergent large-scale phenomena. And so specifically, I think there's a lot that can be done. A lot of my work is about kind of trying to quantify things that relate to the interaction of gas and stars on sort of smaller than 100 parsec scales, but within a galactic context. There's so much work you can do in the Milky Way. It's incredibly powerful, but it's often very confusing. Whereas if you look in stuff in external galaxy, if you can get the small scales, you also get the larger context that those small scales are happening in, and that's an incredibly powerful combination. So fundamentally, if you want to do anything that involves small scales, it pushes you close. And there's kind of like 3 regimes outside the Milky Way that people do this. Do I have a pointy thing? A tiny little pointy thing. Okay. I'm a big fan of the stick, but okay. So like there's the Magellanic Clouds. The Magellanic Clouds are awesome. The Magellanic Clouds are also very huge on the sky. They are a very specific pair of tidally disturbed complicated galaxies. There's the local group, and this is just a subset of sort of star-forming galaxies. And then there's a larger local volume where there's been sort of fantastic work done over the last decade at kind of characterizing a broad range of galaxies. And so basically, this is a logarithmic scale, and the closer you get, the better and better physical resolution you're going to get out of it. Okay. So I'm going to do a fast tour through gas at high resolution, and then I'm going to pivot to talking about the stars. But this is really kind of motivating why I think we're in a really special time to be doing this kind of work. So I want to highlight some of the beautiful work that's been done in the FANGS survey. And so, people in this room, Janice, many others have been involved in this. And so this is a composite image where HST gets you the stars and sort of obscuration from dust and, a little bit of a handle on what's happening with H2 regions. And then JWST is getting you some emission from cool stars, but also a lot of information about the ionized gas and emission from warm dust. And warm dust is a very important tracer in the interstellar medium. So even though it's a solid, it's something that I think of as being very much connected intimately to what's going on with the gas. So Carl will argue with me that dust is not at all the same thing as the gas, but I will use it effectively as a useful tracer of what's going on. At the same time, ALMA has been revolutionary in this work. That FANGS, in a project led by Adam Leroy, has gotten molecular gas. This image has HST image underneath it. They didn't get molecular gas with HST at about 1 arcsecond resolution. And this data is really reaching sort of 50 to 150 parsec scales. And if I were to overlay through vastly superior PowerPoint skills, if I overlaid this onto this, you would see that a lot of this JWST emission is, perfectly lined up with what's going on with the molecular gas emission, which is why, Carl, I'm allowed to say that this is a tracer to some degree of what's going on here. And you'll also see that these features actually are nicely filling in these extinction features that we see with the dust. So, however, if you want to go farther than that in terms of diving down into resolution, it's kind of going to, Legis and FANGS have done a lot of the work about what you can in the larger local volume. So you really want to sort of start pulling into kind of things that you can find in the local group. So when the first multi-cycle treasury came out, I had been doing stuff that was more local volume based, and people were like, "Do you want to do a super duper thing out here?" And I'm like, "Nah, I want to go close." And so that's where we wound up. And so a lot of what I'm going to be talking about from here on out is going to be sort of focused at these sorts of scales, which really are orders of magnitude better resolution. So it doesn't matter what facility you're using, you will get an order of magnitude improvement in your resolution when you're operating in the local group. And you actually cover quite a wide range in stellar mass. There's ranges of physical condition. You cover a wide range in metallicity. So even though it's not that many compared to the wealth of data that's available here, it's still pretty good sampling of what's going on. So one of the things that's been a really big advance recently in the local group that's I've been fortunate to be part of is this local group L-band survey. It was PI'd by Adam Leroy. I'm one of the several co-PIs on it. The first paper was led by Eric Koch, who was at CFA and is now at NRAO. And this is a VLA survey. If some of you remember the THINGS survey, that was revolutionary for having both C and D array. This actually has all of the configurations with the VLA. It's an extra large program that runs at NRAO, and it's getting down to sort of 2 to 5 arcsecond resolution, which is probing scales in atomic gas or the radio continuum between 5 and 20 parsecs. Very exquisite velocity resolution of sub-kilometer per second resolution. These are just the C and D arrays from the data release. These are those local group galaxies that will be making various appearances and what I'm talking about. So this is an incredibly rich data set. I'm very, very excited about the work that we can do with this. So, what I think is that, in the local group, we are really reaching these scales where we're bridging from these kind of scales where we see these emergent correlations in the behavior between gas and stars to really getting down to sort of physical scales where we can start getting at the astrophysics. So, just to give you a sense, this is part of the LMC, and this is 100 parsecs. And so a lot of what you do in external galaxies is usually a few hundred, like a very high resolution. That typical extragalactic survey will be sub-kiloparsec, but not heftily so. And so all of this stuff is happening in one resolution unit. And so the closer in you go, the more you can kind of pick out all of these things. So just to give you a sense of like, one example from what happens in the local group now. So Ryan Chown is a member of the local group L-band survey collaboration. This is NGC6822. The background here is a Galax image. Then it's got this absolutely absurd distribution of atomic gas around it. This is some of the data from the local group L-band survey. And then he focused in with like JWST and ALMA just in this one little section here. Okay, and so this is a JWST and H alpha image, and this is the ALMA image on top of one of the PAH tracers here. But the thing I want you to note is the scale bar in here is like 20 parsecs, right? Like this is real, like that's real, that's getting pretty remarkable. And just to kind of give a little bit of context of it, there's that same image. This is an image from a large ALMA program trying to look at the emergence of molecular cores with ALMA, and it's got a 3 parsec scale. And like, as an astronomer, this is less than an order of magnitude different. So I call these things like basically the same. And so, I mean, so I think like we're getting to a regime where we're starting to really touch base with what's happening in the Milky Way, but in external galaxies with a much wider range of things. And the other thing that's happening that's really beautiful is in the Milky Way, the investments have been getting larger and larger, and they are also building up surveys where there's large programs like this, or ALMA gas, where they've been, doing lots of star-forming regions, and they're actually starting to have samples where they can start to see emergent correlations, as opposed to a lot of, I would say 15, 20 years ago, a lot of Milky Way work was very detailed studies of one individual star-forming region. They now have really large samples, and like we're very close to meeting in the middle. The other thing that's happening is that there is a growing wealth of work happening in the simulation space at very, very small scale. So like in addition to these like beautiful galaxy-wide or measuring the CGM in galaxies, beautiful simulations there are large communities of people that are concentrating on very small scale. So this is the StarForge project with currently being led by my colleague at CCA, Mike Grudich, where these are very small scale simulations of individual turbulent gas clouds that are collapsing. This images, which are stills from this, -10, this is in parsecs. So again, tens of parsecs across this whole region. It has the magnetic, it has, full MHD. It's got radiative transfer in it. It's looking at individual stars, not star particle that, of arbitrary mass. It's got self-consistent thermodynamics. There's jets, there's winds, there's supernova. So really lots and lots of the relevant physics is now being actively simulated on these scales. And so, this is pretty much me, right? Like this is all, we are at a very specific, gorgeous moment in time when all of these things are really coming together, and we stand a chance between both the large surveys in the Milky Way and the stuff that's happening in the local group. Like we're pulling all, and the simulation work, we're all pulling this together. So my focus has really been over the last decade plus has really been about stars, but I'm interested in stars as themselves, and I'm interested in stellar populations is what it tells you about galaxies, but I'm also particularly interested in the interrelationship between stars and gas and how we can use these things together. And this is like, these are deeply coupled systems, right? That if you have stars, they deposit energy and or momentum into the gas through, like they have winds, they have jets, they just send out radiation that can do all sorts of things. Sometimes they can photoionize things. These winds or jets can run into things, and you have processes that are due to shocks. You can produce dust in stars that then contribute back to the interstellar medium. Likewise, when you have gas is the immediate precursor of stars. And so you're going to change what happens with the production of stars through what's the density structure within the gas, what's the internal kinematics, what's the chemistry in the gas, what cooling mechanisms are operative, what level of shielding do you have from all of this environmental stuff that the stars are feeding back in, magnetic fields, which I have come to love. So I suggest you do too. They have really bad like I learned to love dust. I never thought I would love dust, and I adore dust. And I'm actually really coming to love magnetic fields. So please join me in my cult. So anyway, so this is a very, very astrophysically tightly coupled system. And you can't understand the state of the gas without knowing something about the stars. And you can't understand where origins of stars if it hadn't been for the gas. So these things, these things are coupled. Like we see these global things like a Kennicutt-Schmidt relationship, like the higher my gas density is, the higher the star formation rate intensity with a different efficiency. So that is like a large scale emergent thing we know, but somehow that is coming out of what's going on at these small scales with these stars, like, exampled in this Starforge simulation. Remember the Starforge simulation, we are, God willing, coming back to it at the end. Okay, so what I'm going to try to make the case is that resolved stellar populations really give you the means to unlock detailed quantification of a lot of relevant physics on astrophysically interesting scales. But it does require that you and your buddies are going to, you're going to be very busy for a long period of time trying to make this happen. And I really feel like after, probably a decade and a half working on various aspects of this, I feel like finally I'm in happy raccoon mode. It's all starting to really come together, but it's been a lot. Okay, so this fundamentally, I will argue, anywhere outside of the molecular clouds, and it's even helpful in the molecular clouds. I think this has fundamentally been a space-based effort, and it's that the Andromeda galaxy is very close on the scheme of things, compared to most galaxies in the universe. This is the closest large spiral outside the one that we live in. But it's blurry from the ground. If you try to measure, imagine measuring photometry. If I want to measure the brightness, how many stars are they, how bright are they, what color is it? This has been done, and it gets the photometry right for about 6 stars. And then it kind of guesses and makes mistakes for another 10 or so. And this is what you get from the Hubble Space Telescope, right? There's many, many, many hundreds, if not 1,000 stars that you can actually make reasonable measurements here. The color magnitude diagrams look totally different. So basically, anytime you have improved physical resolution, your photometry, your photometric quality goes up, and you just simply see farther and farther down the luminosity function. So the less tightly stars are packed on an instrument, the more stars you actually see. And that's you just keep on going down the luminosity function until you've packed as many stars into the image. So the closer you get, natural spacing of stars is farther you can see finger down. It's a big win. So all of this started earlier with the Angst survey, but the really high resolution stuff started with the panchromatic Hubble Andromeda treasury. You could see from that horrific animation, this took 3 years. It was 800 some orbits. It was a lot. It's 3 cameras, so it truly is panchromatic, so ultraviolet, optical, and near infrared. And it just takes a lot of data because these galaxies are quite close. And so this is the penalty of working very close, is you have to work over wide areas. There's not going to be a Hubble Space Telescope map of the Magellanic Clouds. There may be a Roman or Euclid map of them someday, but something like Hubble, it's too much. And this is a zoom in that gives you some sense about just the volume of data. There's photometry just in that original FAT survey of more than 1/10 of a billion stars that have been detected that we have. You can see the differences in color, you can see differences in brightness, you can see that differences in color are sometimes spatially correlated, probably indicating differences in dust rather than changes in stellar temperature. And they're all at the same distance. It's not the Milky Way problem where, if it's not well measured by Gaia, you don't necessarily know exactly where it is. We know where these stars are with respect to each other, at least in projection. This work is continued. We recently completed the other half. This is the panchromatic Hubble Andromeda Southern Treasury, so called FAST. And my long-term collaborator, who just is fantastic, leads all kinds of things, Ben Williams, came up with a very clever scheme where if you throw out, all these tiles were based upon the infrared chip, which is pretty small. And he had the insight that, Roman is coming. So if we throw out the near infrared, we can tile on the UV, and then we'll just get UV and optical, and then we can be much more efficient and cover a larger area. And so this was like less than 100 orbits or around 100 orbits to do this whole area, which was pretty, Ben's very clever. So this is what it looks like, and it looks like just a nice picture of M3031, but if you zoomed in, it would just look like the other one. And you can see we're now in the region where I chose this part for FAT because it was the uncomplicated, clean version. This is like Andromeda at the highest difficulty setting, and then there's M32 and Ivana. Ivana has sunk years of thinking into what's going on with the stars in here. And there's also spectroscopy associated with this, large groups of people doing spectra of these stars. We then added on M33, only the inner regions. Those of you, someday before I retire, SumTAC is going to grant that there is the rest of the galaxy that's out here. So originally the T in FAT was triangulum because we actually asked to do M33 in the very first proposal, and then they were like, that's a little greedy, so they only gave us M31. So this was very exciting, we finally got it. So this is FATTER, so it's the Hubble Andromeda Treasury Triangulum Extended Region. And again, Ben has led the paper doing the photometry for this. Adam Smarcina, who's in the room, has been a big player in this. And the program that I'm running right now that's in progress is we're now adding in with Hubble those 4 other star-forming local group dwarfs that were accessible with the VLA. And so this is going to bring matched photometry for all of those galaxies that we have the very high resolution H1 for. There are dedicated ALMA and SMA program, like there's a bunch of programs that are going that are really leveraging that VLA investment to really get full ISM tracers across this. So this is showing where the UV imaging is in these systems, and then there is optical imaging that goes on top of it, so it's for filter coverage. The only difference is that IC10 is very low latitude, and so it's kind of hard to work with. So we skip the UV and are doing just infrared for the survey, and then we'll just go back and grab deep UV where we actually need it. It wasn't worth surveying in that. And so these tilings were chosen to get down to H1 column densities of about 3 solar masses per square parsec. So everywhere there's gas, we will be measuring the stars, which gives us, there's a big dynamic range in the gas density, so we'll really be getting gas efficiencies and whatnot and all of these things. I realized when doing this talk, I didn't have a name for this survey. And so I'm test driving this. If people have other ideas, like fold, but like I'd love to get something that was still in the same vein. So if you have an idea,
Vultures.
Yeah, that dates you, Eric. Like I don't know that, so there's an opening in the team if you bring essential skills. Okay, so what do these programs share? Like this is the thing is like we are like really, really close to having 4 to 6 filter photometry in large contiguous areas over all the local group galaxies that have accessible H1 observations with common observing strategies. Like this is pretty remarkable. It's like if you step back, it's like, wow, this is kind of, this was never the grand plan, but we kind of have done it except for the outskirts of M33. Oh my God. Okay. So, I was just also thinking that one of the things about these surveys that's unusual is that these are large areas. Like previously people used to do galaxy formation by like arguing that like if I get these 6 tiles sampling a range of radii, I will absorb, I will then know the complete star. And it's like, there's stuff that's happening on every scale in galaxies. And if you want to look at what's happening on a small scale, it is happening in the context of a large scale. You kind of need all of this. Every one of those galaxies is a complicated special baby. And random samples of it just won't do it. The more you study these things, the more you realize, like, if I had made conclusions based upon just a couple of pointings, I really would have confused myself. The other thing is that stuff, if you're interested in the interaction of gas and stars, that's a very stochastic process driven by small numbers of stars. Lots of the stars that formed are not actual big participants in feedback. So like you need a lot of area before you start getting statistics on this. There's also all kinds of interesting constraints you can get from stellar evolution during the most uncertain phases, and the most uncertain phases are typically rapid ones, and rapid ones means you don't have many stars in that thing because they're just zipping through that part of the evolution space. So you need big areas before you get samples of those. But then you get them in the context of lots of other stars, so you can kind of anchor them like, okay, yes, it's that age, and it has to make sense with all those other stars. Another big one, I don't have time to show, control of systematics, or at least acknowledgement of systematics. In these large area maps where we do repeated photometry of the same kinds of stars, you can just, the systematics jump out, and if you were just taking a single pointing, you would say, oh yes, I absolutely have 1% photometry, and my answer to you is no, you don't. Like, it's very clear when you look at this, and I think there's a lot of room, though, where we can leverage this to improve things, but these systematics are 100% there. The other thing, stars don't actually stay where you're born. Like, we have to acknowledge the existence of binary stars at this point. It is like, and there's very good binary evolution models. So I did Tom Wag is just this remarkable UW undergraduate who's now a postdoc at the CCA, where, like, you know, we ran like every possible plausible binary physics model to track where stars go in realistic potentials. And typically they explode, the typical star explodes like close to 40 parsecs away from where it was actually born. And large numbers of them explode 100 parsecs away from their born. So that there is a physical disconnect between where the star, you think the star came from, and where it actually deposits its energy. So things are complex, and like large contiguous areas really give you at least a prospect of trying to understand about this. So there's a huge amount of science that can come from just measuring the brightness of stars. Like, in the end, we take a lot of HST data and then we just measure a bunch of brightness of stars, and that sounds really not that interesting. It's extremely interesting. So I'm gonna run through sort of some of the basic techniques, and then I'm gonna hone in on the big fun. Okay, it's all fun. Like, there's a zillion talks you can give this. So the kind of workhorse of measuring brightness of stars is the color magnitude diagram. So on, there'll be one axis that's characterizing how bright stars are, and another one that's looking at stellar color, but it's basically a proxy for temperature. So stars occupy different positions in this diagram based upon how bright they are, what temperature they are, and they do it in a redundant fashion because typically when you have a star formation event, you form stars of many different masses that have different evolutionary pathways. So at a given moment of time, if I look at stars of a different age, color-coded by a color here, those stars occupy a specific position in this diagram. So what this means is that there's a lot of redundancy, that when I have old stars, this is where they live, and if I make a prediction based upon these stars, I better get the right number of stars down here. There's a redundant coding on the masses of stars, the evolutionary phase, dust, metallicity. Generally, young star, blue, these are the young stars occupying over here. Older stars tend to be over here. In between is kind of a mishmash. So you can just take this just broad knowledge of where different stellar ages go, and you can break them up. This is work that was led by Adam Smersina, and look at main sequence stars, core helium burning, asymptotic giant branch, red giant branch, and then you can just kind of plot these things that we think have different characteristic ages, and you can see that like the same galaxy looks very different depending upon the age tracer you're applying to this. And this is the lowest level thing you can do. You can go straight from photometry to these maps, and they're incredibly revealing in terms of structure. So like M33, it turns out to be a barred 2-arm spiral, which in its mass, which was not at all apparent from any image. That there have been hints of this in some early near infrared work, but it's very, very clear when you plot the stellar populations. There's all kinds of things you can do with this. You can also do very quantitative things with this. So this is a recent work by Tobin Wayner, who is a grad student at UW, where he's carried on work from that Alexia Lewis did in the first fat region, and then brought it over to the fast region, where you divide this up into little 100 parsec bins, and in each bin you basically forward model the color magnitude diagram. So on that little animation, you can think of each one of those mono age populations as like a basis set. And it's like, how many of these basis sets do I need to have to add up before I make a CMD look like I saw it in this pixel? And you do this, and every single pixel is derived independently, and you see the emergence of very coherent structure in here. And this is quantified. This is where the old stars are, this is where the young stars are. This is in this time interval, this is where the stars that currently overlap that position formed. And so there's a nice movie of this, but the static one works just fine. And what this is, for those of you who are thinking about feedback, this is a spatially and temporally resolved history of energy input into the gas. So I can take one of these things, read off the star formation history, stick it in starburst 99, and I can tell you when did all the supernova go off? When did the photoionizing radiation go off in this? Like, you can just read off all of that stuff once you have this. So this is, and you can do it back in time. Like, one of the puzzles in doing all of this is we see the gas today and we see stars that are forming today. The properties of the gas were shaped by stars that formed previously. Like, it's the integration of that past history. But that past history does leave a record in the stars that we see. So even if it's not forming stars, we can say, yes, there was a big burst of stars right in that region, and that's why that gas, why there's a hole in the galaxy at that part. Okay, so this is very important to be able to connect not just over space, but over time. Now, the filter set that we've used for this, for all of these, and this is my tentative, I should have, really, I will take your submissions. So this is the bandpass. So this is a function of wavelength. So these are ultraviolet, optical, near infrared. This is the basis sort of 6 filters that were widely used throughout this program. And underneath are spectra of stars of different temperatures. A lot of the kind of workhorse, if you're only going to pick 2 filters, 475 and 814 are a particularly good choice to use because they have a pretty wide spread in color baseline, which is enough to tell the difference between an SED that's declining from the blue to the red or one that's rising from the blue to the red. Like, you can separate this out. So if you only have one, this is pretty good over the whole range. However, if you add, you start gaining the capacity to actually start telling some differences between different stellar temperatures, more obscured stars, and then getting the ultraviolet gets you a much better handle on sort of the Balmer jump, which is rich in information, and it also gets you finer constraints on stellar temperature. But the other thing it does, oh, Carl is so happy, is that it also provides enough information that you can disentangle the effects of extinction, that these are the effects of extinction and changes in spectral type can be orthogonal in certain parts. And so for a lot of stars, you can wind up with unique solutions where you jointly solve for the actual like stellar properties and the dust at the same time. So typically characterized by 1 AV, and also so the extinction in the V band, and then also with some sensitivity to spectral shape if you add up regions. In Carl's dream 1 star, like if we got another bluer filter, then we'd be. I know. The dream lives. And Carl's written a very lovely piece of code that is really about doing this sort of inference process. So what's so fantastic about this? I mean, there's many things that are fantastic about this. I'm going to talk stars, Carl. I'm sorry. The dust is fantastic too. Stars are good. Is that you can infer the properties for like literally millions of stars in these systems, and you're translating observable properties to fundamental physical properties like luminosity, temperature, evolutionary state, like interiors. Like, you're actually making inference about stellar interiors at that point. And then if this inference is sound, which really it's proving to be quite sound in most situations, once I know the properties of a star, I can tell you what its flux is in things I didn't observe. I can tell you how much ionizing flux came out, and I can tell you what ionizing flux came out earlier in its evolutionary phase. So once you have this, if you're willing to assume that you have secure enough knowledge about stars, you actually can do incredible levels of energetics at a very like ergs per second at a specific time kind of level. It's very, very powerful. So one of the things you can do is, and this is work that was led by JHU grad student Christina Lindberg, who's now at the CFA, with Claire Murray, myself, Josh Peak, Carl, there are various usual suspects involved in this, is you can take this inference and then figure out where all the hot massive stars are. These are the stars that are principally responsible for feedback. And so this is, if you do selections and you look at where they are, like they're clearly not random. Like this is not some random map about where stars are. Like they clearly know things about the galaxies, even though the inference is done star by star by star. When you look at where those stars are, they're in very, very specific locations. And this is a background map of dust emission, and you can, which is where, if I take dust to be kind of a measure of where cool gas is, it's meaning I find the young massive stars in regions where there's cool gas. So like that's, you know, a line. It didn't have, none of that had to work out, and it just kind of worked out. But the other thing is that in the course of doing this inference, you also get the line of sight extinction to that individual star. So these things are all color coded by this line of sight extinction to this. Now you notice that they're all really pretty blue. Okay, so you're going to stick a pin in this. We're going to come back to this. This is the first ingredient to serious fun. Okay, all right. So the other thing we can do is we can infer the full line of sight column to dust. So this is, the first one was just, I have a star, how much dust was between me and the star. But the second is saying something about what are the statistical properties of dust in small regions where stars might live. And so let me just show you very briefly how this works. So there's features on the red giant branch that are really intrinsically quite narrow in color space. And they're so narrow that there really isn't any physical evolutionary model that can put stars over here. So this is a region that is inaccessible by stellar evolution, except possibly like up here for some very Martha Boyer flavored AGB stars. But like most of this should be vacant. So what this means is the only way that you really can put stars in this region is if they have dust along the line of sight. So the relative numbers and the distribution of stars in this region compared to this region tells you something about what's going on with the dust for individual stars and also kind of at a population level. So these are the stars that are unreddened. This is where we would find reddened stars that are living behind dust. However, in galaxies, not every single, in extragalactic astronomy, we often treat dust as a screen that's just between us and stuff. Here we're talking about systems where the dust is embedded in a highly structured way and probably with small scale height. Like in the Milky Way, an external edge on galaxies, dust has a scale height like associated with the cold gas. It's like 100 parsecs. It's not 5 kiloparsecs thick. The dust layers tend to be relatively small scale things. So when we look at a galaxy like M31, stars are either in front of the dust or behind the dust. That's kind of it. There's very little that are embedded in it except for the youngest, most massive stars. These are all very old stars that are just kind of moving around the galaxy. So these are tracer particles. Okay? And when they're tracing in front of the dust, they're not tracing anything. And when they're behind the dust, they are point samples behind that dust distribution. So if we take, so here is part of the FAT survey. This is a very large PowerPoint table, keynote table, indicating 25 parsec pixels. And if you were to zoom in them through the 2,100 technology, you would be able to see this is a map of the Taurus molecular cloud in extinction. Okay, and so in a 25 parsec pixel, this is 25 parsecs, there is some collection of dust that you could imagine looking something like this. There will be some population of background stars that are doing point samples through this distribution. And some of them might happen to hit a really dusty area. Some of them hit a low dust region and they're still going to be sitting on top of the red giant branch star. But this is a statistical sampling of this. And typically people find in the Milky Way and in simulations that this distribution of densities tends to act like a log normal. So we expect some sort of log normal distribution of dust densities when we sample behind it. Then there's also going to be some population of foreground stars that are in front of it, and they're just blue. They're just like normal vanilla stars. So you can model color magnitude diagrams in each one of these pixels. So this is an actual case. These are the observed stars in a pixel. Here's the unreddened CMD. It's a crap model for this particular color magnitude diagram. But if I add in a component that's behind that has sampled a log normal distribution, which is basically just a convolution of this in color space, then that naturally populates this. And this winds up being a very good physical model for what this distribution looks like. And so it gets you like how much extinction did you have, how much dispersion was in that, so something about the statistics of dust in that region. And it also tells you the fraction of stars that are in front of or behind the dust, which contains interesting geometry information, which I will not get into. And so here's what that looks like. So here's an image. So find by eye some dust features. And then that's a map of it. I'm going to rotate it away. The other thing to note is that you can have regions that don't look dusty, but the regions they don't look dusty is because only a small fraction of stars geometrically are behind the dust. This is impervious to this. This fits that out. And so it can tell you, yes, there is a lot of dust there, and maybe it's only affected 10% of the stars, but it affected the crap out of them, so there's quite a bit of dust. And so this is one of the reasons and the ways that when people do inference based upon color and obscured dust morphology in galaxies, they can get themselves quite confused about what's actually happening, because dust geometry can really change how affected your net color is for this. Okay, so we'll go back the other way. All right, and so it's, again, this is one of those things, each pixel's done independently. They don't have to match any of the structure at all, and they do. Again, not making it up. So we now have two pieces. Oh yeah, we get some time for fun. Okay, so we have these maps that are telling us the statistical properties of the total column of dust. Then we've got measurements of the dust that happens to be sitting in front of individual massive stars. And so the question we're all kind of interested in is like, we think that the massive stars are very young. They're born in molecular clouds. Molecular clouds have a lot of dust. So certainly early on in their evolution, these things should be embedded in a lot of dust, right? Like this stuff is happening. Like think about the trapezium in the Orion Nebula. Like you can't see it without JWST because there's a lot of dust around that. So this is something that we know should happen in the early phase, but we also know that massive stars are big sources of feedback. And so once you get massive stars, we're pretty sure that has some sort of disruptive effect on the molecular cloud that was in, but we don't really know the timescales for these things. People try to measure them statistically, like I count this many molecular clouds that don't have massive stars in them, this many massive stars that don't have molecular clouds. There's all kinds of games that people play to try to get at this timescale. But this combination of data sets really gives you sort of a new way of addressing it. I'm going to talk about some of Christina's results, and then I'm going to talk about some simulations that I think that really turn the interpretation of those results totally on their head that I'm so excited about. Okay, so I'll sometimes use the word embedded versus not embedded or unembedded. Like when you have embedded clusters, you have star formation that's happening, but it's like well behind a lot of extinctions and typically from a lot of different directions. This is, the Orion's already evolved enough that you're kind of blistering out on one side, but there's plenty of cases where you see warm dust, but you can't actually see any stars in the optical. And that's probably like you've got very massive young stellar objects or actual massive stars that are still deeply embedded in that. And then we know that with time, the feedback is sufficient enough that you wind up with things that look like kind of like the Rosette Nebula, or most of the gas is clearly on its way out and empty. Okay, so let me show you how we can get a handle on that. So we have HST observations to individual stars, and sometimes they're behind the dust, sometimes they're in front of the dust, sometimes they're behind a dusty layer, but like there isn't much dust, so a wide range of things. We have data that tells us something about the statistics in the environment that the individual star is in. Okay, so this individual star could be experiencing very little dust in a very dusty region, or a lot of dust in a region that like if you happen to be right behind that, you could have very high extinction, even though most of this is not a particularly dusty region. So they're not the same things. This is a statistical measure of the behavior of dust in that unresolved region. Then you have the line of sight for the dust that's in front of those individual massive stars. Okay, so now imagine there's one picture. If massive stars are, the second you get massive stars, your cloud is destroyed. By the time you see a massive star, it will have already ruined the molecular cloud it came out of. So it might have been in a molecular cloud, but it completely destroyed it. And in that case, you might have statistical high dust, but it might be that like the particular molecular cloud that the massive star was in has already been kind of disrupted, and you'll have like a lower line of sight dust, even though it's a region that has a lot of molecular gas in it. Lots of dust, lots of molecular gas, but like the massive stars are already having a problem. And that's something where it's like very fast feedback associated with it. Like get in the star plume and we almost never see evidence that the stars are still in molecular clouds. Then if the massive stars do not disrupt their birth cloud quickly, so in other words, you can get some massive stars, but it just takes them a while to really cause the damage. So it's like your well-behaved child turns into a very angry teenager late in life, right? then the problems all start. This is, in this case, the line of sight to the dust will be higher than the mean because these stars are going to be particularly picking out the tails of the distribution. So there's the statistical dust, but these things are naturally going to live where stars are most likely to form, which is going to be the high density gas. So in that case, the massive star should have higher than average dust. So I will show you a picture. Okay. So this is a brilliant picture that Christina made where there's going to be points. It's going to show you a map of massive stars, and then the outer circle is going to show you a measure of the sort of typical statistical dust extinction in that region. And then the inner circle will tell you the line of sight extinction to that individual star. Okay. So what you can see here is that the inner circle, it's just yellow. It is one AV. And like this is a very active star forming region. There's like tons and tons and tons of massive stars right here. And it's a very dusty region. Like you can see how black these outer circles are. Pretty much every massive star, except for like maybe that one and that, there's a couple, but like almost all the massive stars have very, very low dust. And so this very much is saying that it's not that if massive stars rapidly disrupt, at least in M31, that disruption is happening very, very, very quickly. And so it perfectly aligns with this scenario. So this, I think, says something that disruption by massive stars is fast. I think Christina's work really nicely shows. And I think to me, this is like a real testament to the power of this kind of resolved stellar populations data. If you think about like all the different ingredients that had to come together to make these quantitative measurements, but I think they're very, like there's a reason a paper like this came out 10 years after FAT data was, this is a lot of higher level science products for our terrific friends in MAST. Okay, so there's a very comforting story of star formation that I think fits in nicely with this. And so I'm just going to run through this, and then the fun comes. Okay, I'm already having fun. Okay, so stars we think are born out of clumps of very cold, dense, dusty molecular gas. Here's a map of molecular gas. This is what it looks like in the optical if you want to be convinced that there's a lot of molecular gas. Okay. The gas is clumpy, so it means when you form stars in this, the stars are clumpy, and then they typically fall in these clusters. Okay. We see a lot of evidence that clusters very rapidly dissolve. Okay, so this is known in the field as infant mortality, that you give birth to clusters and then very quickly, very few clusters last. Like something like a globular cluster that lasts for gigayears is a very, very rare thing. Stars are born clustered, but they do not last clustered for very long. And this is less than 10 million years. Okay, so I think most people agree to some relatively large degree that a big part of infant mortality is the fact that in a lot of the galaxies we study are in a regime where star formation is very inefficient. Even after you form a lot of stars, you've still only used up a few % of the gas. So what this means, as soon as you have any kind of stellar feedback that gets rid of the gas, this becomes unbound. So you have a system that was bound enough that it collapsed, but in most cases, once you get the stars to form, that gas is just going to go out. And you can say, is it winds, is it supernova, is it photon, is it whatever, but stellar feedback certainly, we know empirically, removes the gas, then it's gravitationally unbound, and then stuff expands. Okay, so this is a model that we have in our heads where stars are born out of gas, the gas leaves. So in my mind, and I would argue in many people's minds, is that if I have this picture, it naturally translates into this evolution in the embedding. Right? That the dust and gas are pretty coupled, and once I get rid of the gas, I'm getting rid of the dust, and that's why there's this change in obscuration. Right? This is like This makes perfect sense. I slept well at night. This is also wrong. And I love it. It's so interesting. Okay, so so Center for Computational Astrophysics has a program where graduate students who are working on their thesis can come. Tobin Wayner is a UW grad student who had been doing like observational stuff related to stellar clusters and the IMF in some of the data that we have in M33 in particular. But he wanted to do some like simulation kind of stuff, and so he came to CCA for 5 months. Mike Grudich is the scientist who leads that StarForge collaboration, so that beautiful simulation of that individual star forming region. And so just to warn you, we are switching from data, but it's really good. So here's a single frame of the StarForge simulation. Hopefully that beautiful movie is seared in your mind. If you take that single frame and you do full radiative transfer to make pretty images, and you rotate it, this is fixed time looking at different viewing angles. And you can ask, like, what is the time, what's the amount of extinction at a given time overall for every star and also for every individual star? And then how does this change as a function of time? And so Tobin was very interested in, like, how fast is that emergence from being deeply embedded in these sorts of simulations? You can see from the, how the amount of extinction you see is definitely dependent upon viewing angle. And so Tobin does some kind of angle averaging to try to characterize what that extinction is. So here's a bunch of different snapshots, and in every single time step for many different viewing angles, he calculates for every star that exists, what's the line of sight extinction. Here's 3 different viewing angles, and things like here, lots of stuff is extincted. Here you get some clear views of stuff. So this is kind of the basic characterization for every star. Then if you look at the ensemble of stars, and this is the fraction of stars that have a high AV. So here we're saying IV greater than 1. AV of 1 is about where you start to get CO shielding in a solar metallicity galaxy. And you can see that at early times, which is like less than, so this is characterized in free fall times. This is 2 free fall times. Basically everything has some high AV. At late times, only a small fraction of stars have high AV. And then there's this intermediate period where it's changing rapidly, but it's, half, plus or minus half a free fall time. And it's, in terms of clock time for this particular simulation, it's like 2 million years. It's super fast that you go from nearly everything has some amount of extinction to like everything is pretty easily spotted. If you go to a higher extinction level where it's more about like high density gas tracers, happens a little bit earlier, but it's that same really fast kind of decay. Okay. So that's the basic behavior, and so that's like agrees with this fast notion. But where it got really interesting was Tobin made like this it's a baller plot. So now he's tracking the individual stars. So that was like the statistics, what fraction of stars are extinct. So then he started making some plots of looking at the time evolution of every single star as a function of time. And he wrestled a lot with like how you decide what time is in this. What mass do you use? Is the mass at the current time, mass at the final time? And so I'm going to walk you through these. Okay, so this is a complicated plot, but we're going to break it down. So this is log of AV. This is 1 AV, so this is that sort of CO thing. So this is showing the typical degree of obscuration, and this is a function of stellar age, which you. So on this AV scale, this is 10 AV. So these are things that are like pretty much invisible in the optical and certainly in the UV. JWST could probably get a fair number of these. And then these are stars that you're just seeing them in all their naked glory. If you notice in terms of stellar age, what he chose to do, which was pretty brilliant, was he set 0 time. Since stars are forming throughout the simulation, the wall clock is less interesting than how are individual stars evolving. And so he set 0 age as the time when stars reach their maximum mass. So during this period of time, the stars are still growing in mass. On the other side of this, the star is as massive as it's ever going to be. Okay? And so this, he makes this plot at every single time step here. There's a gray area here, which are just times that are not accessible. There hasn't been enough time to get to that part. And then they are color-coded by the final mass of the star. So not the current mass. So this star here is still accreting mass, and its destiny is to be a relatively high mass star. Okay. There's a histogram up here that tells you the stellar ages at the current time step. This shows you the median AV for individual stars. So this is like a classic Seaborn plot. Up here, massive stars are going to be colored purple. This is the median age of all the stars. All right. OK, so here's the animation. We're going to watch it, and we're going to break it down. Like, stuff's going on. Like, this is a lot more informative than that average thing. OK, we're going to go through it once, and then I'm going to break down sort of what's happening. OK. So the first thing is that stars of high and low mass are forming throughout the simulation. There's not something where it's like it goes on, it gets high mass stars, and then everything shuts down. OK, there are changes in the overall star formation rate, but I would say that within sampling, I don't think that you're any more or less likely to get a massive star pretty much anywhere in this distribution. It just kind of keeps on going. And so what this means is that as gas clears in the simulation, there's still pockets of cold, dense gas that are capable of sustaining star formation. So like that continues to go on. Okay, the typical extinction of formed stars, it does drop with time, right? So this is what we saw in the net thing, and this is what goes with our intuition, is that this distribution goes down, and by now most of the stars are relatively easy to observe. Okay, and so this does reflect that comforting story of ongoing gas loss and ongoing mass for the cluster as a whole. Okay, but this is the thing I want you to concentrate on. What's happening at 0 age? This is when stars stop accreting mass. They're up here at high extinction, and then they tend to drop very, very quickly when they hit this. Okay, especially the massive stars. Okay, so what this is that the accretion ending is kind of about, I've lost my local gas supply, right? If I think about stars increasing in mass, I'm in an individual molecular core and I'm just gobbling stuff up. And when that process stops, that's when the extinction drops. And to me, what this means is that the extinction causing the obscuration is incredibly local. Like, imagine an alternate universe where all the extinction was in a shell out here, and then stars inside that shell were doing their individual little accreting things. If their accretion shut down, they'd still have the same total accretion. The fact that these two time scales are bang on top of each other says that the extinction and the embeddedness is like right on top of the individual massive stars. It is not the thing as a whole. And the second they stop accreting, the reason they stop accreting is because they start having enough feedback, they start having enough winds or radiation pressure to shut off the gas accretion, and that ruins that that blows out the molecular cloud. So this says that the feedback is super, super local. And if you look for contrast, like the low mass stars just kind of drift across this boundary. There's no particular change. Like, they are not affecting, whether they're accreting or not, is not really affecting anything about the environments they're living in. But the massive stars very strongly affect their environments. Okay, so if you look at like the average mass accretion history or AV history in different bins of mass, you can see that the massive stars actually get more extincted with time because they've got this runaway collection of stuff. And then bam, feedback turns on, they ruin that, they stop accreting, and then they just kind of evolve based upon the mean gas density. So the massive stars are shutting off their own local gas supply, which is what dominates their embedding. So what this means, and you can see this in individual mass tracks, like it's just like they're just shooting up in mass and then it just stops, right? That's when like the local feedback turns on. So it means that this picture is not actually the step where the embedding is stopping. What's actually happening is that the stars that actually dominate the light, like these are the massive stars, these are the players in terms of all of your emission measures, they clear their own local gas. So there is overall still some global feedback that's going on, but in terms of the embedding and the obscuration, that is happening very, very locally. So what this means is that the global gas destruction or expulsion is not really the dominant player in feedback, which was like shocking, but in retrospect, it's like, oh, that's a consistent story. And the massive stars, they just don't spend time at intermediate extinctions. That's why when you look at it, they all have an AV of 1, because it's like by the time you saw it as a massive star, it's like it was done. Okay, and then just one final, like, there's other non-obvious implications for this. So one of the things that also kind of like Tobin was working on this and it was like, oh yeah, that makes sense. So Tobin made this beautiful plot showing, first look at these labeled areas. This is showing the distribution in different phases of hydrogen as you go across simulation time. And early on, things are in kind of like cold, dense forms. At late times, things are mostly ionized and some of the gas is gone. So like that all fits with our thing. But if you look at where the H alpha is peaking, it's peaking really, really early. It's not when you actually have most of this ionized gas. And the reason is that recombination radiation is a density squared process. And so where you get that H alpha is when those few massive stars early on in the cluster light up. The gas is still dense, so the recombination rate is really high, and so the H alpha emission spikes. You do get emission from H alpha later on, but like it's in very diffuse gas, n squared is small, it's not super luminous. And where you actually get the most H alpha emission is right on recombination of the photodissociation regions that just trace where the molecular gas is. So this is a very different picture of everything that I thought. JWST, just really fast, really good for young stellar objects. That really pushes you into this early region. So like you can actually get this, and they're also, you can go lower down the mass scale than like H alpha. And so you get a less stochastic thing. You can get a better measurement of that. Also just want to credit Eric Bell, Adam Smersina, and Ben Williams, who did a really great job of showing that JWST can actually do fat in the local volume. Just, there's some galaxies that are close enough that you can actually do this. And because they're more distant, it's a lot more efficient. It's not as expensive as fat, but the higher resolution lets you go out a little farther. Thank you. Sorry I went long, Ivana.
Questions for Julianne?
I'm sorry to go late. I know people have to take kids.
Yeah. Well, we'll pick a few and then you can
Okay. All right.
That's but let's see. You and the red sweater.
Great talk. So it's nice to make the connection between the simulations and the stars and gas. And it's a plausible picture, but it seems like it's not fully closed in some sense. So that inference from the simulations that the destruction of the dust is very local would seem to have different implications for the IR emission from the dust than if it weren't local. So there may be a testable infrared prediction of that.
Yeah, and there are tests in the paper showing sort of like the time history of like 20. What would you get if you inferred from 24 micron? I think it comes down to, these are not like the Starforge models are not models of this specific star formation region. So, and they're very expensive to run. And so it's hard to say statistically what happens. So I think that will always be a weakness, but you can run lots of different kinds of simulations with different physics in it and see, does this hold when, you turn various knobs. But I think a lot of the, generally lots of stuff is n squared. And lots of emission processes are n squared. And that, I think, really drives you to the importance of very local things. And to me, I think it really does make a lot of sense that the moment that a star is gobbling and increasing mass, that's got to be the time when it has a very, very high local density. Otherwise, it would not be undergoing runaway accretion. And if we are expecting these stars to remove all the gas from the cluster, it's certainly going to start with its little nubbin of gas before it goes full jihad on like the rest of the cluster. So I think there's some stuff that I will be kind of surprised if it's not transferable. But I do agree that yes, the dust emission is an interesting part of that story as well.
Eric, you had your number.
Yeah. Thanks for the jam-packed.
I know. I'm sorry. It's a lot.
No, thanks for that. But I just want to ask a follow-on question from your very last slide,
which is suppose you can continue your streak and you get 800 hours of Have World's time. You just reuse your acronyms because the reach is there, or do you find new environments or do something completely different?
So one of the things that I'm concerned with observationally and theoretically is we've made so much progress, I think, in understanding what happens in the self-regulating mode of disks. Like there's a lot of, like we've got self-regulating bathtub models, we've got beautiful observations, we have simulations that seem to do a very good job on a lot of this. A lot of important star formation in the universe happens out of equilibrium at very high densities, high external pressure from gravitational binding, in environments where it's largely shock driven. Like elliptical galaxies are not forming stars like this. And I think there's a lot of people who study sort of like ULERGs, and again, a lot of that is far enough away that you are really kind of stuck with this population level inference about things and much less about how does gas at those extremes behave, how does star formation at those extremes behave. And so I think it's really a very good time to take these, there's a lot of people simulating ever better Milky Way disks. And I think because of the high register, like Shyam Menon is a postdoc at CCA, and he's really like leaning into trying to do more JWST-ish conditions. I'd like to see more star formation in merging systems where you have very, very strong shocks and deep potentials. Like I think theoretically is kind of how we're going to gain a lot of insights, because I think it's going to take something like Hab Worlds or Hab JWST, like because it's going to take even bigger. But that's something where I think actually, I think there's going to be a lot of progress that will come from 30-meter class telescopes. And I think the 30-meter class telescopes will do better than Hab Worlds at the longer wavelengths that you actually need. Like if you wanted to look in the center of something like ARP 220 to really suss out what was going on, the 30-meter telescopes might actually make a really good stab at that. But I think there's a lot of room in simulation space to build some intuition for how things might go.
So I know that more of you have questions, but I don't want to keep people that much longer.
And it's my fault. I'm very sorry.
Yeah, so I encourage you to please ask your questions to Julianne and let's thank her one more time.
I'm around. Well, I was under an hour, so I